My pleasure to introduce the next speaker to you, Professor Sebastien Glaser from CARSQ at Queensland University of Technology, Australia. And Sebastien is going to talk about artificial intelligence and autonomous vehicles, understanding local context. Thank you, Sebastien.
Thank you very much. Let's start. When we are discussing about automated vehicle, very initially, it was a kind of silly idea from the researcher. We have a very nice topic to manage, and it was something that started very early. I am not going to do a history of the automated vehicle, but you can look at it's not something that started 10 years ago. It's something that is quite far older. However, recently take a very different dynamic. And when we are looking at automated vehicle, we are looking at improving a broad range of sectors and improving the efficiency of transport, of access to mobility and mobility. So there are plenty of advantages that have been captured by the industry in order to understand and to continue the development of automated vehicles. However, this is an infographic from Accenture, which is 2 or 3 years old. However, it's still very accurate. If we are looking at who's developing the automated vehicle technology, and especially the self-driving cars or autonomous cars or whatever name we are giving to them, there are 3 different areas worldwide where this technology are developed. In the US and North America, in the broad Europe, and in Asia. So this is where most of the experiments and most of the development took place, very simply because you have car manufacturer, you have equipment suppliers in this area, and they are driving the research and funding this kind of research. I'm saying cars because this infographic is only capturing passenger car, or mostly capturing passenger car. And in fact, there is a broad range of other vehicles that are automatized, and they are developing some building components related to localization, to avoidance, to environment sensing in order to make this vehicle happen. And they may take different forms that does not look like exactly what you may imagine as being an automated vehicle. But for instance, the farming industry, for years, they have their tractor which are able to localize themselves and to replicate a trajectory when they are in the field in order to harvest, in order to plant crops and things like that. In the mining has a very, very well developed automated vehicle strategy. They even reach a point where they are thinking at a concept called zero entrance on mine sites, where they have no human interaction as long as there is no emergency on the site. So this hauler, they are 200-ton vehicle that can transport minerals from the ground, from the very low level of the mine up to the processing plant with absolutely no human intervention. No human intervention on site. They also develop a very broad strategies of remote operation and remote control of this vehicle. Obviously, we have a very broad range of new type of cars, such as the small shuttle and medium range shuttle, or result of new type of urban vehicle, because if you are speaking about autonomous car, you no longer need to have a steering wheel in your car, and you may improve the space drastically. Another area where autonomous technology is developing quite strongly is the freight industry, because of the shortage of driver, but also to improve the transport efficiency in that site. And if we look at how automated vehicles are behaving and are working. I usually refer to this very schematic diagram about automated vehicles. There are many different blocks and many different functionalities that an automated vehicle has to achieve. But now, under these different parts, so there is one first block called OEDR for object and event detection and recognition, which is looking at what happened in the environment and try to understand what these objects are doing, what these obstacles are doing, classify the obstacle and determine the future path, so that we can have a set of tactical functions which are planning the trajectory of a vehicle. And the challenge now is that with the recent developments in the amount of data that we have and the computational capabilities that we have, they are driven by machine learning, and more specifically by deep learning strategy. So if I came back to the title of the presentation, a most honest title would have been Deep Learning and Automated Vehicle. And it's where a lot of challenges rise related to understanding local context. Not going to do a full course about machine learning. However, how this deep learning is operating, you have a large data set where you have labels on these data sets. So for instance, you have an image and you say this is a cat, and another image and this is a dog, or you have a nice bounding box around the cat or the dog. You train and you tune the parameters of your system, and the magic happens. After that, you present an image of a cat, you say it's a cat, or if you fail training your system, it would say, I don't know, or it's a dog. But usually you can manage to achieve a very good accuracy with the system in terms of recognition, in terms of object classification, in terms of trajectory prediction. They are very efficient tools in order to understand what happened in the environment, to determine future trajectory or to determine the behavior of what you are observing, but also to create your future trajectory of your vehicle. However, the main problem of that and the main challenge is that in order to tune the parameters in your deep learning system, you are using a training data set. And this is where most of the challenge is, because obviously the strongest limitation you have is that the answer you're going to provide through your system is what your system has been trained on. So if you have something which is close to your data set, it will provide an answer which is very accurate. If you have something that is far from your data sets, then you don't know what the answer will be. And you can't predict that answer. So if we came back to this figure about where the automated vehicle and the technologies are developed, we can see that there is a huge focus on several areas, which are obviously not covering the whole world. And it's where the adaptation to local context is becoming challenging. So obviously, there is a quite known problem of the kangaroo, how to detect and to understand kangaroo, which is a very strange animal because it's not always linked to a very specific position on the ground. It is jumping a lot of time, and it has a very crazy behavior. You can't hardly predict what will be the next jump of a kangaroo and when this next jump will happen. Another problem that we may not see quite directly, it's not exactly related to local context, but it's related to how a new mobility device or how something new happens in the driving environment. Bear in mind that your vehicle is designed to have a lifetime of 15 years. And look now, in the past 15 years, what have been the evolution of the mobility environment. 15 years ago, you don't have any e-scooter. And if you build a vehicle 15 years ago with a detection mechanism based on deep learning, and that this deep learning obviously is trained on a worldwide database, this worldwide database doesn't include the e-scooter. However, here you have an example. If you have a system which is trained to detect pedestrian, then you will see a pedestrian. However, this pedestrian will have a very strange behavior. And if you still have the ability to detect an obstacle, then the problem will be how you can predict its future movements. So a pedestrian, for instance, usually works with a speed of 3 to 5 kilometers per hour, unless this pedestrian is running. But an e-scooter can drive up to 25 kilometers per hour, even more, but depending on the countries, there is a lot of regulation. So just imagine your system, it say, oh, I see a pedestrian, and then you give this information to your next function. You say, I have a pedestrian here. You will say, okay, this pedestrian is likely to have this future path, and I will try to avoid this future path, obviously. But then your pedestrian is not working at 4 kilometers per hour. It is working at 25 kilometers per hour. It's a very, very good pedestrian. It is working very quickly. It's not only related to the perception and to the detection and classification, it's also related to the way we plan trajectory. And there was a very, very interesting experiment called the moral machine. However, it was mostly focused to the trolley problem about how a vehicle has to decide crashing into different type of person or different type of objects with different outcome. However, what is interesting related to that is that depending on the geographical area, the answers were very different. It means that the concepts of trajectory, the concept of planning a trajectory will differ between the different parts of the world. And it's where you need to adapt locally. You need to understand what are the specificities, and you need to have a system which is able to capture this difference. So with the Queensland Department of Transport and Main Road and the iMOVE Australia, we have built a very long project in order to understand what is the specificities and how the infrastructure is ready. So this was a two-part project. The infrastructure readiness was led by Professor Michael Milford at QUT and was investigating whether how infrastructure can be understood by an automated vehicle, and the final report of this project is available. So you can have a look at it on the iMOVE CRC website. And the second part of the project that I am managing and that Professor Andrew is leading is about how an automated vehicle will fit into the environment. So we have two Renault Zoe. The first one is a sensing platform, and the second one is an automated vehicle. This development of the automated vehicle was made with Renault and Vedicom, and it allows us to have driving permits. So now on this second part of the chat project, we are looking at different dimensions. We are looking at the driver dimension, meaning how driver reacts to automated vehicle. We are looking at the use of CITS messages. In parallel to this project, there was a very large experiment related to the deployment of CITS messaging in a local area close to Brisbane. This is the ICVP project in Ipswich. And we were looking how an automated vehicle can benefit from these elements with using the existing set of Etsy messages. The work package tree, which is the main focus of the presentation, is about the Australian specificity, and I will come back later. And the last one is about the public awareness. So in order to improve the public awareness, we were conducting some large experiments in order to invite the public to test and to evaluate and to understand what the automation is. For most of these work packages, we have finalized the data recording, and we are now evaluating the safety benefits. So very briefly for work package 1, we had 72 participants who experienced the automated vehicle on a test track. By experiencing an automated vehicle, I mean they were seated in the driver's seat and they were fully in charge of the automation, to engage the automation, to react to the demand from the automation. And when the vehicle was in automatized mode, the driver was able to have non-driving related tasks, whatever task he is willing to do. We had very strange condition. We experienced a very nice tropical rain for almost a week, which forbid us to continue the experiment, because the very heavy rain that we had looks like having a Christmas tree around our vehicle in terms of obstacle detection. The droplets of the rain were very, very large and limiting the detection and sensing from our vehicle. We had very nice encounter with very few wallabies and monitor lizards, which are let's say between 60 to 80 centimeter lizards that were working on the track. And so the participants were seated in the driver's seat for 30 minutes, and the full automation or the full automated parts were for about 25 minutes. We have two groups, one with a low condition where they were expecting just, where they were experiencing just one takeover request, and the other group were experiencing up to 5 plane takeover requests. We look at different data from the driver in order to understand how fast they were reacting, and what was their first response to a takeover request. So the main results were about the duration of a takeover request, which was about 3 to 5 seconds, depending on the driver, with some tails in the distribution up to 10, 12 seconds. We continue this experience now with new non-driving related tasks, new environments, condition, and new traffic condition in order to see how this takeover request evolved depending on the non-driving related task where the driver was involved. The very last one we had, the driver while monitoring the driving of the vehicle has to look at a quite complicated video and answer at the same time at a questionnaire about the video and about the technical aspect of the video. The takeover request and the takeover time increased drastically, far above the 5 seconds that we had in the second one. The work package 2 we were using, so I was mentioning existing automated existing CITS messages in order to convey some information to the vehicle and to be able to use this information to plan future actions. So here is an example where we had hopefully the video will work so now. Here we were using the DNM messages related to roadwork, and these DNM messages as an optional field related to alternate paths, and we were using this optional field in order to provide an alternative path to the vehicle, and we successfully managed to integrate this and test this on a test track. The very last one just to show you the kind of experiment and the kind of driving we were doing. So this is in Bundamba, close to Ipswich and Brisbane. And we had participants going into the vehicle. The road was fully open to the traffic. There was no limitation about what other driver or pedestrian can do. And the vehicle was evolving in the city for a bit more than a week in order to have participants and use this in order to convey and to understand how people react to the automation. So last is our main interest today. It's about understanding what are the specificities in Australia. In order to do that, we use this diagram, which is from the Velicom MOVE project and Pegasus project, in order to understand and to define with a group of experts a very specific scenario in order to understand how the vehicle may understand this scenario and has to react to this scenario. And recently, I must highlight that there are similar works being conducted at the IEEE. It was initially a working group for proposal, and it's transformed into a standard for creating assumptions on how the other road user reacts so that the automated vehicle can understand some reasonable assumption about the driver, about the other road user behavior on the road. So it's this standard provide a formalism in order to describe this scenario and to describe relevant variables about this scenario, such as the distance between the other road user, the vehicle, how this other road user reacts, what the acceleration speed, and what the consideration we can have about how this is changing. So I was mentioning we were using quite similar approach in order to determine the scenario. So the very first part was about the road safety analysis of Australian road to find what's different type of scenarios involved during crash and how this scenario differ from existing scenario worldwide. And we also have a lot of discussion with road experts and road safety experts in Australia, and specifically in Queensland. From that, we determine 13 high priority scenario and 6 which are lower priority. But we wanted to be sure that this scenario were really unique for Australia. So the second phase of this study was to invite international experts to discuss with these international experts about our methodology, but about the finding as well, and to select with them or to rank with them what are the very specific scenario and how we can continue our study in order to have a better understanding. So because of the budget, we had to select 2 or 3 scenarios. Obviously, there is a first one, which is well known from everyone, and I already mentioned it. It's about the wildlife. The second one is one that I discovered myself as well in regional Queensland. It's where you have a one-lane bidirectional road, sealed road, with a very large shoulder. So these roads are quite frequent, and you can find them quite frequently. The problem of this road is that they are not only used by passenger car, they are also used by truck, by long vehicle, and by road train. So you can see approaching on this one-lane road a vehicle which is as wide as the lane, and you have to avoid it, which is completely crazy in terms of how you have to program this in an automated vehicle. So the understanding of the situation and the reaction to the various situations under the scenario were completely crazy from the automated vehicle perspective. And obviously, the very last one, which is the one that I'm going to develop, it's about the road train. So road trains, road trains, they are heavy vehicle, long vehicle that cruise regional Australia in order to transport cattle, minerals, and they cruise these roads with this very specific truck that are hardly seen elsewhere. Where did we do our recording? So we have several roads around Brisbane and a bit further than Brisbane. Since the beginning of the project, we have recorded about 20 terabytes of sensor data in various weather conditions, day and night conditions, various traffic conditions. We had a very specific focus on an area with truck, long vehicle, and exceptional convoy, where we had done more than 70 trips in order to see variability related to the weather condition, related to the traffic condition from a vehicle perspective, not from an infrastructure perspective. And we went west of Brisbane, so we went to Dalby, where we had a lot of road train being captured, which is 300 kilometers west of Brisbane, and Charleville is 800 kilometers west from Brisbane. And this is the kind of data collection we were conducting. So obviously we didn't go that much on unsealed road with this vehicle. It's really not, there is no photoshopping involved in this picture. However, the size of the vehicle, the type of the suspension is definitely not designed accordingly to this type of road. However, it was very interesting to understand how the vehicle reacts in this condition in terms of what is the dust impact on the sensor, what is the vibration impact on your algorithm. So we created an on-road driving data set, and thanks to the Antimpera IVS software, we were able to use automatic data labeling and annotation from our data recording, so we can focus very quickly on specific scenario and scenario of interest for our one. So these are the road train. So road train is a combination of a prime mover and multiple trailer, up to 4 trailer. The size of this vehicle can reach 53 meters. So it's about between the double and the triple of the size of a truck you can commonly see on your road. And it can weigh up to nearly 140 tons. Obviously, given the size, given the weight, the dynamic of this vehicle is very different. It has a low deceleration capability, and obviously it has a far longer stopping distance. And if you look at the sensors and how sensors react to this vehicle, you can see that classic algorithms are not able to manage and to understand what this kind of truck is, and especially when you are using clustering algorithm on point cloud, you barely manage to capture the full size of the truck. When you are looking radar, so it's not very, maybe not very visible, but when you look at radars, the radars only capture axles of your truck and not the full truck. However, we have very good visualization of that. So we don't want to develop a system that is completely able to manage, but because of the relationship of the project with the Department of Transport, our goal is to understand how in the future this kind of truck may present an obstacle to the deployment of automated vehicle. So very simply, we were using a YOLO V5 in order to understand how these trucks are seen without being clearly labeled as a road train. And they are mostly seen as trucks and detected as trucks. I mentioned, which is quite fun given the name of this type of vehicle, sometimes they are seen as train. So we can easily avoid this kind of detection because it's very unlikely that a train is on a sealed road in this kind of region. So we developed several strategies in order to integrate this vehicle in the classification. Should it be by refining and extending the number of classes in the training of our YOLO system, or to add an image classifier at the end of the detection mechanism, because we know that most of these trucks, of these road trains, are seen as a truck, and to be able to see them. And similarly to the proposal for the IEEE standards, we also analyzed what was the main relation that a truck, this kind of truck, have with the other traffic participants. And we were looking, for instance, at the distribution of time headway, depending on the position of the truck around the vehicle, and how the vehicle, how the truck reacts, do overtaking maneuver, and is maybe creating a danger for the automated vehicle. In the future now, and in order to conclude, we will implement this strategy, and we will go back into rural area in order to see how our strategy to understand and to react to this vehicle is working. And in the future, we are looking at further use cases related to the Australian specificity. I was mentioning the one-lane bidirectional road, but also, which is a very challenging situation in Australia, all the flooded roads. Thank you very much. And this is a picture of our friend, which allows us to do the video recording in the cars at us. Goodbye.